Welcome back. In our previous slice of physics, we looked at constant acceleration motion, and we understood a lot about the motion by studying the graphs of that motion. And in doing so, we stayed away from numbers and equations. Well, it's now time to look at the equations of constant acceleration motion. We will get familiar and comfortable with the equations of constant acceleration motion so that we can apply them in upcoming problems. So let's begin with the equation that corresponded to the definition of acceleration. We had ax equals delta vx over delta t. Acceleration was nothing but the rate of change of velocity. So it was a change in velocity over time duration. Now change is always final minus initial value, so I can rewrite this delta vx at the top as vxf minus vxi, final velocity minus initial velocity, and I still have delta t here in the denominator. I'm going to just rewrite this here without the vector notations. I'm going to leave them out going forward, but you know which quantities are vectors and which are scalars. So I've just simply rewritten that here. And now if I multiply both sides by delta t and add vxi to both sides, I will get my second equation. I get vxf equals vxi plus a times delta t. Why do we need different forms of the same equation? Well, they're useful in different situations depending on what we have and what we want. If we want to find the final velocity of an object, knowing the initial velocity, the acceleration, and the time duration, this second equation is important. If I have the change in velocity and duration and I want to find the acceleration, this first equation is important. What if we wanted to get displacement for a motion with constant acceleration? Let me move over to graphs here to derive this based on our previous knowledge. We know that displacement is area under a velocity time curve, and if I have a velocity time curve that looks like this, that corresponds to a constant acceleration. The slope of a straight line is constant. And now I'm going to take a time duration that starts here and ends here. So this difference here is my delta t. And if I want to get displacement in this duration of time, it is equal to the area under the plot, between the plot and the x-axis. So this area is the one I'm interested in. I'm going to shade it in over here. Now this is a little bit of an awkward shape to get the area off, so let me divide it into two parts that we are more familiar with. Now I got a rectangle and a triangle, and if I add those two areas, I will get the total area under that plot, which will be the displacement. So I'm going to shade in the rectangle in one color and the triangle in a different color. Okay, given that displacement is this total area, what does it turn out to be from this graph? Oh, let me mark some more points over here. So this is the initial velocity for the motion that I'm interested in finding the displacement for, and my final velocity is over here. By the way, I should have labeled my axes, so I'll do that now. Velocity there and time there. So now displacement is the sum of these two areas. So let me start with the rectangle. The area of the rectangle is simply the base times the height. In this case, my base is delta t, and my height here is vi. So I got vi times delta t is the area of the rectangle, and the area of the triangle is going to be 1/2 times the base, which again is delta t, times the height, and the height here is this value. And you can see from the graph that this total value here, the full height, is vf. The short height is vi. So the height that I'm interested in for the triangle is simply vf, let's call it vxf, minus vxi. So let's be consistent with our other equations here and work with the right subscripts here. So I'm going to fix that here as well. So now this vxf minus vxi is simply delta vx. And delta Vx from this first equation is simply Ax times delta t. So I can do some rearranging here to get delta x as Vxi times delta t plus 1/2 Ax times delta t squared. The reason I get squared is I got one delta t from this term, and I already have another delta t that's multiplying into it, so that's what gives me the delta t squared. So that's my third equation. This is useful in getting displacement for a constant acceleration motion if I know the initial velocity, time duration, and the acceleration. And my final equation, I'm not going to derive it, but I can tell you that using these two equations, we can eliminate delta t. Just solve for delta t in this equation and plug that into this equation and simplify algebraically, and that'll give me Vxf squared equals Vxi squared plus 2 times Ax times delta x. So this is useful if I don't know the time duration for an object, but I know how far it went, what the initial velocity was and acceleration was. This is useful in solving for the final velocity. So all of these equations describe constant acceleration motion. The one you want to use depends on the situation and the problem and what you know and what you want to get. And in the next video and our upcoming work in class, you will see several examples where we will use some of these equations to solve example problems. So this slice of physics was dedicated to understanding the equations of constant acceleration motion. In this course, it's not important for you to memorize equations of physics. I'll always give them to you when you need them, but it's your responsibility to understand and apply the equations correctly. That's where a lot of students have to do some work. So these are the four equations that we worked with today for constant acceleration motion. They may look a little bit different to you on the screen, but that's simply because I have eliminated the subscript x. We traditionally use subscript x for motion along horizontal direction, y for motion along vertical direction, so sometimes we can use different subscripts, or sometimes we can just use them without subscripts as I have presented them here. We got the first equation that deals with the definition of acceleration. The second equation is simply rearrangement of that to get the final velocity in terms of initial velocity, acceleration, and time duration. The third equation is useful for getting displacement based on initial velocity, acceleration, and time duration. And the final equation was useful when we did not know the time duration.